Okay, we're going to plot a few rational numbers on a number line. So the rational numbers that I'm going to plot are 5, 3.87, and negative 17 over 3. So I've got 0, and then 1, 2, 3, 4, 5, 6. And then negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. 5, we'll color code this. We'll put 5 in blue. 5 is simply an integer, and that's exactly where 5 is, and that is called plotting 5 on a number line. Put a little dot at 5. The next number is 3.87. So 3.87 is more than 3, but less than 4. So 3.87 is going to be much closer to 4 than it is to 3. I'm going to estimate it to be right about there. More than halfway for sure. That is 3.87. Notice how I'm color coding, so I don't need to write the number above it, but I'm going to anyway. So that if you're using pencil and you're just doing what I'm doing, you at least have the value above the dot. And then we have negative 17 thirds. So let's do this one in a nice bright green here. Negative 17 thirds. Negative 17 thirds is going to be to the left of 0. Now to find out where negative 17 thirds is, I'm going to need to divide. So negative 17 thirds is going to be the opposite of 17 thirds. So I'm going to rewrite this as the opposite of 17 thirds. So I'm going to figure out where 17 thirds is first. Where is 17 thirds? 17 divided by 3. 3 goes into 17 6 times, 5 times. 5 times 3 is 15. I subtract and I have 2 left over. I can put a decimal place here and then bring up that decimal, bring down the 0 and continue to get a better estimate of how many times 3 goes into 17. It's going to be more than 5. 3 goes into 20 6 times, which is 6 times 3 is 18, and then I bring down 20 minus 18 is 2, and I'm going to bring down another 0. 3 goes into 20 6 times. 6 times 3 is 18, and I continue to have this remainder of 0. So what's going to happen is 6 is going to repeat. So I'm going to get 5.6 repeating, which is about 5.7. And remember, we had the opposite of 5.7. So I've got the opposite of 5.7. So I'm going to look at 5.7. 5.7 would be closer to 6, but we're going to have the opposite of that. So it's going to just reflect over 0. So negative 5.7. Negative 5.7 right here. So you can see 5.7 is over here. It's going to reflect over 0. The opposite of 5.7 is going to be right here. Negative 5.7 is not quite negative 6, but it's closer to negative 6 than it is to negative 5. So that's where you get the opposite of 17 thirds, or negative 17 thirds. So kind of a neat way of looking at plotting a negative number. Okay, decimal notation. I just showed you decimal notation, so this is called decimal notation for 17 thirds, or the opposite of 17 thirds. That's what we did. Let's practice a few here. So let's try decimal notation for 11/6. So 11/6, we're going to write this as a decimal. So we're going to actually do the division. So we're going to take 11, make it the dividend that goes inside. I'm going to write that out for you. The dividend is on the inside. The divisor is on the outside. And then we have a quotient plus a remainder over the divisor if we write it as a fraction, or if we're writing it as a decimal, we're going to ignore this part and we're going to make decimals and add zeros at the end. Okay? But you might remember that plus the remainder and go, what was that called? Okay. I'm gonna need this room potentially, so I'm gonna erase all that. 11 divided by 6. I know I'm going to need some decimals, so I'm gonna put 11.000. I have not changed the value of 11. I've just added some decimals with zeros at the end. I'm gonna bring up that decimal place. Now I'm going to divide normally. 6 goes into 11 once. 1 times 6 is 6. Subtract. 11 minus 6 is 5. And we're going to bring down this 0. 6 goes into 50. Thinking 7 times 6 is 42. 8 times 6 is 48. 8 times 6 is 48. Subtract 50 minus 48 is 2. Bring down the 0. 6 goes into 20. 3 times 6 is 18, and that is a 2. Bring down that 0. 6 goes into 20. Again, 3 times 6 is 18, and this is going to continue forever. So when I say this is going to continue forever, I mean the 3 is continuing forever. So 11 over 6 is the same thing as 1.8, and then just the 3 is repeating. So we put a bar over the 3 to show that just the 3 is repeating. This is a rational number because 11 is an integer divided by 6, which is an integer, makes it a rational number, which tells us that we're either going to have a decimal that terminates on its own or a decimal that repeats a value at the end or repeats a pattern at the end. And this pattern is a 3. So 1.83 repeating. Let's try another one. Let's try 1/4. So 1/4, you may already know what 1/4 is a decimal. If we don't, we're going to take 1 divided by 4. And that dividend, we're going to put a few zeros after the decimal place. We're going to bring up that decimal place. Then we're going to say 4 goes into 1 0 times. 0 times 4 is 0. 1 minus 0 is 1, and then we're going to bring down the 0. 4 goes into 10 2 times. 2 times 4 is 8. 10 minus 8 is 2. Bring down the 0. 4 goes into 20 5 times. 5 times 4 is 20, and we have a remainder of 0. When we have a remainder of 0, that means our decimal terminated. So 1/4 is the same thing as 0.25, which is 25 hundredths. So I'm going to have, you've got your tenths, and then you've got your hundredths, and you've got your thousandths. To the left of the decimal, you've got your ones, your tens, your hundreds, and I'm running out of room, so we'll just stop right there. Now, if we want to graph each irrational number on the number line, if we want to graph each irrational number on the number line, I'm going to use this space right here. We need to know the value, the approximate value of the irrational number. And you can use your calculator to do this, or you can use the idea of perfect square roots. Okay, so we're going to be talking about square roots. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, and so on and so forth. So if I have the square root of 1, that's the same thing as 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. The square root of 49 is 7. And the square root of 64 is 8. If I have an irrational number, let's say the square root of 10. The square root of 10. Where would I plot that on a number line? The square root of 10. Well, first I have to say, where is the square root of 10? The square root of 10 is not between, I'm going to resize this and I'm going to change its color. I'm going to change its color so it's noticeable. There we go. The square root of 10 is not between the square root of 1 and the square root of 4. It's not between the square root of 4 and the square root of 9. It's between the square root of 9 and the square root of 16. And it's much closer to the square root of 9 than it is to the square root of 16. So the square root of 10, while it's an irrational number, because it's not a perfect square, it is going to be closer to 3 as a decimal than it is to 4. So if I'm plotting the square root of 10 on a number line, I'm just quickly making a number line here. The square root of 10 is going to be between 3 and 4. Now watch this. This is some pretty nifty stuff here. So the square root of 10 is going to be closer to 3 than it is to 4. It's going to be closer to 3 than it is to 4, but it's not quite 3, so I'm going to put it just to the right of 3, and that's the square root of 10. So plotting an irrational number on a number line isn't too difficult if you can make yourself a nice little table. And sometimes you're going to have to go out further than the square root of 64. So how would I know what comes after the square root of 64? Well, the next number after 8 is 9. 9 times 9 is 81. So if you need to make this go a little bit further when you're working with these problems, you'll write the integer and then you'll put its square inside the square root. 10 would be the square root of 100, and 11 would be the square root of 121. And sometimes you're going to have to go out a lot further than you may have learned when you were learning your multiplication tables. So you may have to go out to 13, 14, 15, or even 25, or 37. And that's where sometimes memorizing and expanding our facts is helpful, and other times using a calculator isn't too bad.